Okay guys, we are back for more energy. We will be looking at some gravitational potential energy and how that ties into our kinetic energy today. Okay, today we are going to be looking at gravitational potential energy. Now you guys may remember I abbreviate that as GPE when we're writing that on the board. And we'll be looking at kinetic energy. So the idea behind gravitational potential energy is that this is the energy that's stored based on an object's position in a gravitational field. So if we have a rope that's attached to a really heavy box, and that is lifting the box from where it starts to some new height up at a constant velocity. So our box is going, well, up, right? Velocity is constant. So what does that mean when we're talking about a constant velocity? That tells us that acceleration is 0. This is a very sneaky way of saying, hey, there is no net force. If there's no external net force, then we're looking at energy being conserved. And we're going to get to what that really means, nuts and bolts of it all. But just be aware, velocity being constant starts us down a rabbit hole of tons of information. So, our box is a system. So the box is moving at a constant velocity. There's an upward tension force in the rope that's equal in magnitude to the downward gravitational force. So what we have is, if we look at the box, the free body diagram, we have a tension, we have a force due to gravity, and it should be attached, and these should be equal in magnitude, opposite in direction. Again, net external force is 0. Now this rope is doing work. Remember, in order to do work, you must go the distance. Work is the force that is parallel to your direction of motion times the distance or the displacement you have traveled. So the rope is doing work. It is changing the vertical position. So what do we know? Well, we know that work is the force parallel to the direction of motion. That's going to be the tension on the rope. Tension of the rope on the box. Okay, what is our displacement? Well, it's going to be some d, which is going to be, looking here, it's going to be y final minus y initial. Now, here you may see that they used the version of this equation which is force distance cosine theta, using the dot product definition. My tension is up. My box went up. So I know that cosine of theta is going to be cosine of 0, and that is 1. So that can drop out. We can just look at how is this in relation to that direction of motion. So that means that the work that was done changing that position is the tension force times this, right? So what else do we know? Well, we know that that should be counter to the work that was done by the force due to gravity, because again, velocity is constant. The change in the kinetic energy has got to be 0. Velocity is constant. So what do we know? Well, here, what is TR? Well, we said that that was equal and opposite to the gravitational force. So that is going to be where this MBG comes in. So it tells us that the potential energy we started with, based on our position, plus the work that was done raising it up, is equal to our final potential energy. So we have just increased our energy store by basically mg times our change in our height. This is what we've done. We've changed our energy stores. So what does that mean? In a nutshell, what that means is that the gravitational potential energy As we said last week, UG, U sub G. The gravitational potential energy of an object in an Earth-like system is mg times its height, mgh. Here we're using mgy. Now, that means that we have to declare a zero level. Something has to be zero. Typically, if we're on the Earth, we're using the surface of the Earth as zero. But here's the cool part. We don't have to. We can declare something else to be zero. We just have to be very, very clear. So we don't have to conform to the norm. So, this is the great part. The origin of our system of coordinates gets to be our pick. We just have to be consistent with the math, consistent with the physics based on that choice. So what are our units of gravitational potential energy? Well, that's the same as the units for work. It's a joule. That is our energy unit. It's a joule. So let's look at kinetic energy real quick. So we have a cart is a system. We apply a force onto the cart that changes the velocity. That is an external force to the system. So we have done work. And that work is going to equal the force that we have applied times the distance we have moved that cart. That is the work we have done. That formula that you're using here is that work is equal to the change in kinetic energy. We've gotten faster. See, increase in kinetic energy. So, what does this mean? Well, let's go back and let's look at some of the basics here. So, we've got the force of the hand on the cart. That's going to be mass of the cart times acceleration of the cart. That's the force of the hand. So this is going to be mass of the cart times the acceleration of the cart times the distance the cart has traveled is going to equal the change in kinetic energy. And you're like, okay, but how do we get from all of this? So where are we getting this from? Well, what is acceleration? What is the distance? We can go back into terms of our kinematic. So where is it all coming from? Well, let's go check. So one of our bread and butter kinematic equations was that v squared equals v naught squared plus 2a change in our displacement or change in x. So this I have right here, this magic little black box, right? So let me solve this equation for what I've got in this magic little black box, or in this case, red box. So I've got v squared minus v naught squared is going to equal 2a times distance. So that means 1/2 of v squared minus v naught squared is equal to a times the distance. So I'm going to put this in over here. So I've got mass of the car times 1/2 v squared minus v naught squared. This is your v final right here. That's where this term comes from. And then you have mass times 1/2 times the initial velocity squared right there. So what we do is we could use kinematics and forces and go, hey, look, the kinetic energy is 1/2 mv squared. M is the mass of the object. That is going to be in kilograms, guys. And v is the speed relative to the chosen coordinates. Again, that's going to be in meters per second. We're back to our standard SI units. That's going to give us a unit for kinetic energy of a joule. I know, shocking. So let's look at an example here. So the Mystic Timbers roller coaster in Ohio has a drop of 33.2 meters. Guys, that's close to 100 feet. The maximum speed of the coaster at the bottom of this drop is 53 miles per hour. So we want to know, can we say that all of the work done by the Earth on the roller coaster is converted to the coaster's kinetic energy during the ride. Okay, so here's something we need to think about is what is our system? So we want to look at the work done by the Earth, so we need to kick the Earth out of our system. So the only thing that's going to be our system, if you look at the little dotted lines here, is just going to be the actual roller coaster cart. So Earth is not in our system. That means there is no potential energy because Earth is not in our system. So let's start by, we're going to go ahead and create an energy chart. So we're going to look and do a work energy chart. So if we do a work energy bar chart, what are we going to get from here? Pen. So we're going to have that the initial kinetic plus the work done should equal the kinetic final plus any change in internal energy. Ideally, that would be 0 if everything went straight to kinetic energy. So initially, the roller coaster is at rest, so that means this is at 0. Our work is going to be, well, mgh is going to have a bar. That's going to be the height we are up. Our kinetic final is going to be that 1/2 mv squared. And I don't know what this change in internal energy is. I need to see. If it's 0, then everything works out perfectly. But we're not sure yet. So, this is where we're at. We start with this formula, our bar chart. So we've got this, and maybe a bump. That's the question. Do we have a bump or not? Okay, so here we go. So we've got the mass of the cart times G times H. Now, if this internal energy is 0, if this was all perfect, this is going to equal 1/2 mv squared. So I don't need to know the mass of the cart. That tells me that my velocity should be ideally the square root of 2gh. What is the square root of 2gh? So it's going to be the square root of 2 times 9.8 times my height. That drop was 33.2 meters. So that's going to give me a velocity of about 25.5 meters per second. Now, the trick comes in the fact that our speed was given in miles per hour. So we know that we were dealing with 53 miles in 1 hour. So 1 mile is going to be about 1,600 meters, and 1 hour is going to be 3,600 seconds. That's going to give us a speed of about 23.6 meters per second. So the speed at the bottom is lower than expected. So that means that some of our energy has to go somewhere else. And that's where it's going. It's going to that change in internal energy. So we could actually calculate how much energy was lost. Obviously in terms of mass, but we do have some energy lost. So there is a change in internal energy. Maybe the cart got heated up. Maybe there was friction on the track. So right now we're saying, hey, everything's ideal, but in real world it's not.